Chapter 5 is statistics, and it'll primarily be descriptive statistics. In other words, collecting, organizing, and presenting data. Inferential statistics will be a little bit in Chapter 6, and we'll still do some descriptive statistics in Chapter 6 as well. So for now, all we're primarily interested in is collecting and presenting data. So the first thing we need to see in a statistical study is that we're usually interested in a population, the entire set of objects or people or measurements or whatever it is we're trying to gather information about. Sometimes it's impractical. Most of the time it's impractical to gather measurements from an entire population. So instead we'll consider a sample or a subset or a subgroup of that population to represent the population in general. Now, to ensure that there's no bias in our sample, one method of doing this is to take a random sample. In other words, just in such a way that we don't prefer any single individual over another, and we just select a subgroup of the population without any sort of bias or prejudice to how we gather individuals or objects. Random sampling within cohorts might make sense sometimes. If a university has 30% women and 70% men, then perhaps our sample should be comprised of 30% women and 70% men. Balancing out the sample to match the population in some sense also makes sense, but within cohorts, we should certainly still randomly sample. So in that example, you should still select randomly among the women and randomly among the men. Okay, so the rest of the population sample and statistical study design can be found in Chapter 5's textbook sections. Now, just to do some calculations and some data organization work, let's consider a few things. Any piece of data is called a data item. It'll often be a measurement, typically a numerical measurement. If that's the case, it's called quantitative data. It can be represented as a number, and it can be called a data value. One of the first things we're going to do is deal with the frequency distribution. That's what we'll see below, to determine how frequent a certain category of numerical data might arise or quantitative data might be distributed. And well, let's get started on the example below then. So they ask us to construct a frequency diagram for the data showing final course grades for students in a pre-calculus course. So our data is listed here, and we have a table to fill out down below. So first thing we can do is we see that our categories are letter grades, so we can fill that in. Oftentimes this will be already filled in, so that makes the job a little easier on the student. And then on the right, we just count up the number of times an A occurs. In other words, the frequency of an A. There are 4 A's in the list above. So there's our 4 to go into the table. For B's, we have, looks like 4 B's as well. C's, looks like there are 6. D's, it looks like there are 2. And there are 2 F's. So a frequency table is as simple as that. You count up the number of elements from each category, A's, B's, C's, D's, and F's, and you put their frequency respectively on the right. So on the left, this is not quite quantitative data, A through F. It's a bit more qualitative since those aren't represented with numbers, but we could fairly easily represent those with numbers if you think about letter grade scales, 90 through 100, 80 through 90, or 89, things like that. So these are called bins typically. Most commonly we'll see the word bins, but they can also be categories or classes off on the left. And that is our basic frequency distribution. So let's see relative frequency. Okay, relative frequency distributions involve the relative frequency of our category items. So anytime we see relative frequency, we should remember that this is very similar to the relative frequency probability calculations we did before. These should always be decimals, numbers between 0 and 1. It's relative frequency because we're looking at the number of occurrences in a category or frequency in a category, and we're dividing that by the total number of observations, measurements, or occurrences, or we could think of it as the total frequency, counting up all the items in the list. Okay, and that will certainly be a number between 0 and 1. Now, this example asks us to use the 5-letter grading scale to form a grouped frequency distribution for the given grade. So the 5-letter grading scale, and they say find the relative frequency and cumulative frequency of each category. All right, so the relative frequency has been defined. We'll work out the cumulative frequency within the problem. So our bin is the 5-letter grading scale. So let's say 90 to 100, 80 to 89.9, 99 repeating. Let's see, 70 to 79.9. Similarly for 60s. And here, we can actually go 0 to 59.9. Our bin sizes should always be the same. It's okay if they're not in this case. We'll just lump everything in the bottom bin together. In a histogram, you certainly want to see that your bin sizes are the same. In this table, we'll just sneak by with not filling out the last 4 or 5 entries on the table that we would need, get all the way down to 0. So for 90 to 100, we count up the number of 90-something grades. There's 1, 2, 3 of these. Okay, so since we have 3 of those, we place a 3 here. And relative frequency is just that, it's relative. This 3 is relative to the 15 total entries that we have. If we counted all of these up, we'd see that there are 15 of them total. So 3 out of 15 is 1 out of 5, or 0.2 exactly. You don't need to put all this work in here. This is really a sufficient answer. Just the decimals are typically what you need, but certainly pay attention to what a problem asks for in terms of the specific answer type. Now for the B's, how many B's are there on the list? There are 1, 2 B's overall, 80-somethings. So that leaves us with 2 out of 15. And this is approximately, we'll just round to 2 decimal places, 0.13. Again, the decimal sufficient, rounded as appropriate as the problem calls. 70 to 79, there are 1, 2, 3, 4 70-somethings on this list. Oh, 5 70-somethings on this list. So clear that. 5 out of 15 is 1 out of 3, and that's approximately 0.33 using wavy equal signs. A wavy equal signs to indicate approximately equal. 60 to 69 is, here's a 68, so that's 1 and 2. So 2 out of 15 once again. This is approximately 0.13. And lastly, 0 to 59, we have 50, 47, and to 57. So there are 3 of these. So 3 out of 15, and that's exactly equal to 0.2 once again. If we were to add up all these fractions, we'd realize that we get 50. Add up all these fractions, we'd realize that we'd have 15 over 15 equals 1. That should always be the case when we add up our relative frequency table, just like a probability distribution. For our cumulative frequency, this is actually a little bit easier. This is just a running tally of how many items have been accounted for per each category. So for the first line, it's always just whatever our frequency was for this category. Okay, so we copy that from the left. Now, stepping down, we'll add this 2 to the current 3 that we have in the cumulative list. So that's 5 to fill in this line below. So here's 5. And then add this 5 to the line above, to the cumulative line above. So we get 10. And this 2 to 10 to get 12. And to finish it off, we'll add the 3 in the numerator to the left to get 15. This number also should match our total. It should always be the same as the total number of items once we get down to our last line in our cumulative frequency. So that's it for cumulative frequency as well as relative frequency. Pretty straightforward things once you know what you're being asked to do. Next is a histogram. So construct a histogram for the numerical grade data given below using the 5-letter grading scale. In this case, we've actually split things up by units of 10. So these are our bins down below, 40 to 49.9, 50 to 59.9, so on from 90 to 100. So we've picked a bin to represent every grade that we'll possibly have on this list. There are no grades in the 30s, no grades in the 20s, or anything lower. So there's no reason to include those bins. It's possible we could, but we don't need it, so we'll cut that off. So for a histogram, we always have frequency on the vertical axis, and histogram is essentially a bar graph. When we're drawing them, I'm not too picky about drawing them with the bars touching, but it is appropriate for the bars to be clumped together. Anytime StatCrunch, the software we'll use to make statistical graphs, or MyLab presents us with a histogram, we'll have the bars touching and all those requirements will be met. So the 40 to 49 category, there's only one grade there. So the frequency of this, represented by a bar, is a bar of height 1. From 50 to 59, we have 2 grades in that category on this list. So with these two, you can draw this bar. 60 to 69, there are 2 grades in the 60s. So again, another bar of height 2. 70 to 79, there were 5 of these. So our tallest line, of course, in forming this histogram, the reason we chose 5 was because that was where we had the most. That was the most frequent, or the largest frequency we found in any of the categories. And from 80 to 89, we have 2. So again, a bar of height 2. And then from 90 to 100, we have 1, 2, 3 of those grades. So here we'll have 3. So there's our histogram for this grade data. It's that straightforward, and most of the MyLab problems that we'll look at, these things will be built for you already, and you just have to match the data to the histogram. Also, StatCrunch will help us take a list like this if it's given to us, and we can have the computer generate these histograms for us automatically. We might be able to select our bin sizes in StatCrunch, but we'll learn all of that in Mini Project 5 this week. Next is a frequency polygon. So it's somewhat similar to the histogram. In fact, if the histogram's handy, if you've already made it, you can form a frequency polygon pretty easily. This is with the same data we had in the previous example. So remembering it, we had 1 data item in the 40 to 49 range, and now we just place a point instead of a bar. We had 2 in the 50 to 59 range, 2 in the 60 to 69 range, 5 in the 70 to 79 range. It might help to look back and recall that this was truly the case for these categories. There were 2 80-something scores, and there were 3 scores in the 90s. Once all the dots are placed, the last thing we need to do is connect them with a line. What's formed is a polygon, a set of points connected by straight lines. Technically, I guess this would finish the polygon off, but that's not necessary. So there's our frequency polygon. Kind of like a line graph, but it involves frequencies. That's what makes it a frequency polygon. Next is correlation. So correlation is a relationship between 2 variables. In other words, if one quantitative variable grows larger in value, will another quantitative variable grow larger in value along with it? Or will it grow smaller in value? Or will there be no effect? So the first 2 of those is a correlation. The second is non-correlated data. So below we're asked to consider in this example, the data is the set of average height of girls versus their age graphed as a scatter plot. So the scatter plot are the points, the dots in this picture. Graphed on there is the line of best fit. This is computer generated. We'll learn how to do this with StatCrunch and or Excel in the future. It's nice to be able to have this and see whether or not this data is linearly correlated or otherwise. And the first question they ask is there a correlation? Well, when we look at the data, it does seem that as we increase in height, in other words, or sorry, age, as age gets larger, it seems like we're moving upward on the y-axis, or the height in inches here. So if that's the case, if we move positively in the x direction and positively in the y direction, like this line is doing, then we have a positive correlation. Okay, so that's the first thing we can write below. The data is positively correlated. And the second question is, well, they don't ask if it's weak or strong. They say what kind. Yes, that's positive correlation. That's what we're answering in that question. Now, in terms of weak or strong, one place to look for that, what you're really angling for, is a line that is nearly 45 degrees if the units are matched up here. These units don't match, the scale's off by a little bit. But it turns out that this does, since it has a pretty good slope. In other words, you don't want your line to be too flat. If it's too flat or horizontal like this, that's no correlation, because if your points are just randomly scattered around this line, well, it doesn't seem like the effect side to side has any effect on where they are up and down. So that's uncorrelated data in that case. In this case, it looks pretty clear that as we move to the right, there's a nice gradual shift in the behavior of this. So it seems pretty strong in terms of correlation. The data is strongly correlated. Another place to see this, both of these pieces of information, is in the equations that we have listed off to the right here. So what we see, and this is again computer generated and sometimes provided, but if we have it, it's a great tool. We see that this number here is the slope, m times x, in the form y equals mx plus b of a line. Okay, this number is positive. Since that number is positive, it means that the line is positively correlated, or the data is positively correlated. The slope has positive, or the line has positive slope. So that's a good hint. If there was a minus sign in front of that and it was negative, then we know that it was negatively correlated. Now, below it, how well correlated is it to the line, or how well does it fit? Does the line fit this data? This is a number from 0 to 1, 1 being 100% correlated. In other words, every dot is exactly on the line with no error whatsoever, down to 0, which is perfectly random noise. The dots are all over the place and nowhere near the line. So if our R² value is, I don't know, probably anything higher than 0.7 or 0.7 or higher, we can say that's fairly strong correlation, or even strong correlation. You might think of it as overall course grade. 0.7 is 70%, and that's just enough to be passing. It's not exactly knocking it out of the park, and it's also not exactly strongly correlated or very close to the data, or the line's not very close to the data. So use that as a rule of thumb. There are some exceptions, but I think that's reasonable for now. So the R² value tells us how close the line is to each point. And in this case, it seems pretty close, and that kind of backs up that there's a fairly strong correlation of these data points of age versus height in girls. Okay. Last, correlation does not imply cause. Okay, it's oftentimes just a coincidence, or there is some background reason for this to be the case. So the example that we look at now is to consider the observation that nations with multiple TVs per household, so multiple TVs per household, have a lower infant mortality rate than those with no or only one television per household. Okay, it seems a little bit ludicrous, and they ask, is there a causal relationship between these two variables? Well, no way does it seem likely that there should be a causal relationship between the number of televisions in an average household and the infant mortality rate of a country. So, but the observation that they're stating looks something like this. So in a scatter plot, each of the points that we put down is going to represent a nation, essentially. So it's feasible that some nations will have between 0 and 1%, or 0 and 1 televisions on average in their households. So, and what they're saying is that there's a higher infant mortality rate the lower number of televisions you have in your household. And each of these dots is representative of a nation, and we're just kind of making it up. It's not likely that any nation has anything more than 6 televisions per household on average. That seems like a lot. Now, this is our scatter plot, and what it seems to be suggesting, and we're just kind of representing what's being stated in the problem above, is that there's a negative correlation. As we go to the right, as the data down at the bottom on the x-axis increases, our data along the y-axis decreases. In other words, to look at it in the context of the problem, higher infant mortality rates occur over here, where there are fewer average numbers of TVs in households in the nation, and on the other end, the more average numbers of TVs we have per household, the lower the infant mortality rate. So it's a negative correlation that they're describing. Is there a causal relationship between these two things? Well, if we just looked at this graph and we were being somewhat ignorant about it, we might say yes. It does seem that if a nation has a larger number of average numbers of TVs per household, then their infant mortality rate is lower. It must be something about the TVs that causes that. Well, no, it's not. What is more likely is that the average number of TVs is positively correlated to wealth of a nation. So in other words, the wealthier a nation is, the higher the average number of TVs per household. So to wealth, and wealth is negatively correlated to infant mortality rate, which means that the more wealth that a nation has, the lower its infant mortality rate must be. And that makes sense because there's more money for healthcare. Negatively correlated. And if average numbers of TVs is positively correlated to wealth, and wealth is negatively correlated to infant mortality rates, then average number of TVs will also be negatively correlated to infant mortality rates. It's a bit of a transitive process there, but I think we can see how that would work out. Thus, we have the correlation observed. Okay, so that it doesn't claim a cause. All it does is say, yes, it's okay for these things to be correlated, and it makes sense, and probably a way to link the two is to just look at the wealth of the nations involved and see what those correlations look like. We'll probably find something along these lines. Again, we're never going to assert causality based on correlation. It's just not our jobs to do so. It's beyond the scope of this course, and it's something you can really get in a lot of trouble with in general. So correlation does not necessarily imply cause ever. Okay, so that's it for chapter 5. There are some extra bits here that you can find in the book and an extra practice problem or two here at the very end. I'll leave those to the student. Good luck on this chapter and see you in the next one.